Assalamu alaikum everyone, this is me Shoaib, and in this video I am going to talk about three-phase power measurement by two-wattmeter method. So from the title of this topic we can understand that we will use two-wattmeter to perform this experiment on the topic. Okay, and the system is three-phase. Okay, in three-phase system we have two types of connections. One is star connection like this, and another one is delta connection like this. So for the analysis of this video we will use the star connection only. Okay, and we can also do the same things for the delta connection like this, but if anyone interested, then you can comment below and I will try to make another video on delta connection. Okay, so now you have a three-phase system. Okay, and you have the lines here, and if I name the lines, then I have to name like A, B and C lines. Okay, and this is the neutral line, and I think there is no work of the neutral line here. Okay, now if I ask you to measure the power which is consumed by that three-phase system, then what you will do? First of all, you will take two wattmeters, and let's say name W1 and W2. Okay, then you have the lines, and you have to take one common line among these three lines to give the connection. Okay, then you will have a probe or wire from the wattmeters, and you have to connect these two wires in one common line. Okay, and you have to take that common line. So in this video I am taking that common line which is B line. Okay, and I am giving the connection like this. Now this W1 will give the rating, let's say W1, and this wattmeter will give the rating W2, and you just have to add these two values to get the total power consumed by this three-phase system. This is the simple case. Okay, and you get the reading and you just give me the reading and your task is done here. But if we try to analyze a little bit, then we have to talk further. Okay, so let me refresh all of the things and go a little bit further. What will happen for the wattmeter W1? I have already told you that I have marked these phases like A, B and C, and at this point the voltage is VA compared to the neutral obviously, and in this point the voltage is VB, and in this point the voltage is VC. Okay, and the current is flowing through all of the lines will be like IA, IB and IC, and obviously in star connection we know that phase current and line current is equal in magnitude. Okay, so in a balanced system all of the voltages and all the currents will be 120 degree apart, in balanced system. So now we have to know that what is the wattmeter equation. What is the wattage equation? Wattage equation is W is equal to the voltage that the wattmeter will read, V, the current through the current that will flow through the wattmeter, I, and the cause of the angle between the voltage and the current. Let's say this is theta. Okay, this is a simple equation of the power, but what power equation will be for W1? This is the question. For the W1, W1 is measuring the power measuring the voltage between VA and VB, so the voltage will be VAB, and the current flowing through the wattmeter W1 will be IA. Okay, and we have to take the angle between VAB and IA. Okay, obviously it won't be the theta. Okay, it won't be the theta, it will be something, so we have to find this angle. This is our task here. For this reason we have to move into the vector diagram. Okay, so now going to the vector diagram, and let's say we have to take the reference values or reference vectors. Let's say we are taking this VA, VB and VC for the reference. If I do VA here, then VA will lead VB by 120 degree. This is 120 degree angle. Similarly, VB will lead VC by 120 degree also. And again VC will lead VA by 120 degree also. The scheme is something like that, when you are drawing sinusoidal waves like this. This is VA, and this VA is leading VB by 120 degree, and also VB is leading VC by 120 degree, and apparently VC is also leading VA by 120 degree. This is the system. Okay, this is the system is drawn here. So now in these types of three-phase system, the loads are generally in inductive type. So if I say VA compared to the neutral, this is the phase voltage. The phase currents will lag phase voltage by some angle, because this is the inductive load. Okay, so let's say these are the current vectors IA, I, B, I, C, and these currents are lagging these phase voltages by some angle, let's say phi. This is also phi, this is also phi, right? So this phi is actually the power factor angle for the particular phase, and all the phi will be same, because this we have taken this system is balanced. So this angle will not be phi, because this angle, this phi is the angle between VA and IA. So this is not our target here to put. Here we have to put the angle between VAB and IA. So we have to find VAB from this vector diagram. So first of all, we have to know what is VA. VA is nothing but the subtraction between VA and VB. Okay, so if we just flip this VB by 180 degree, then VB will be seeing something like this, minus VB. And then if we add these two vectors, then we will have VAB. This is VAB. And this total angle is 60 degree, and if we divide this angle by 2, then we will have 30 degree. So you can see that the angle between VAB and IA is 30 plus phi. Okay, so here we have to put the value 30 plus phi. Okay, so now what we have come to know still now, W1 is equal to VAB into IA into cos 30 plus phi. This is it for now for W1. And what will be for the W2? For the W2, W2 will measure the voltage between C and B point. So the voltage will be VCB, and the current flowing through the W2 is IC, and obviously we have to get the angle between VCB and IC from this vector diagram. Okay, so let me take another color. I'm taking red. Okay, so for this reason, what is VCB? VCB is the subtraction between the voltage VC and VB. Okay, so we already have it is something like this, VC minus VB. So we already have minus B here, and if we add VC and minus V, then we will have this voltage which is called VCB, right? Now we need the angle between VCB and IC, and from this vector diagram we can easily predict that, this is the angle 30 degree, this is the angle phi, and this is the angle between IC and VAB, which is what? 30 minus phi. Okay, so we have to put this value here, 30 minus phi. So this is these are the two equations for W, which is W1 and W2. You can see two equations. Now if we add these two equations, then what happens? W1 and W2 is equal to, let's say, let's say all the line voltages are equal. That means VAB, VCB, BA, whatever is equal, which is VL. Let's say the line current and phase current is equal, normally let's say IL. Okay, so we have to write that VL IL cos 30 plus phi. This is for W1, and for W2 VL IL cos 30 minus phi. Okay, so if we take these parts common, then we left what? VLIL bracket cos 30 plus phi plus cos 30 minus phi. Okay, here we should stop. Okay, now we have to we have to do a further calculation. For this reason I have to erase all of the previous things, not all of the, just the things from here. So if we jump from this line, then we write, if we add these two values, we just simply can get the value √3 multiplied with cos phi. Okay, if you calculate, I have not much enough space to do calculation, but if you calculate at your own, then you will get the value √3 into cos phi. Then the rest of the thing is VL IL. So if I just rearrange and write these things, then we should say, I should write √3 multiplied with VL IL cos phi. Okay, and W1 plus W2 is equal to the W, the total power is consumed by this three-phase system. Okay, so I think you are very much familiar with this equation. When we have the line voltage and line current, and the per phase power factor angle, then if you multiplied all of the things with √3, then you get the total real power is consumed by the three-phase system. Okay, so it's in step by step I have tried to make you understand how actually the 2-wattmeter method works for measuring the power of a three-phase system. So this is it for now. If this video is helpful to you, just do like and do comment and just share. Okay, this is it for now. Thank you for being with me. Bye bye.